Hello everybody, welcome. Let's have a look at these past paper questions dealing with calculus. Alright, start with question 1. Consider the function f of x equals x squared minus 3 over x, where x does not equal 0. And the first question they're asking us to find f prime of x. And this prime tells us that we want to find the derivative of f of x. So how do we find f prime of x? How do we find the derivative? We have in our formula booklet this right here. They tell us if we have some function f of x and it's just some general term, let's just say it's some x raised to the power of n. If we take the derivative of this, f prime of x, what we're doing is we're grabbing the exponent, multiplying it out in front, so now it becomes n times x, and this n, which used to be our exponent and we multiplied it out in front, we decrease it by 1. That's our derivative formula, and it's in, I'll bring it up actually, it's in our formula booklet right at the very end, topic 5, calculus, right here. That's exactly what they're saying. Some term, x raised to the power of n, what do? Multiply it out in front and then decrease it by 1. Okay, so let's go back to the document and see if we can work out the derivative. I guess just looking at this is a pretty common kind of question that the IB often provides. They'll put a variable, in this case an x, in the denominator. That's at the bottom of a fraction. And if we look at our actual formula, everything is just on one level, for example. Doesn't mean that we can't have fractions, but it means that our variables can't be in the denominator. We need to express them just to an exponent, some power, but they can't be at the bottom of a fraction. So we're going to need to work with this negative 3 over x. So let's go ahead and deal with just this 3 over x for a second. I'm going to write out the function. F of x is equal to x squared minus 3 over x. And let's look at this negative 3 over x for a second. So this negative 3 over x, actually let's just keep it as 3 over x. Let's leave the negative out for a second. This 3 over x is equal to, actually let's keep the negative. Negative 3 over x. This is the same as negative 3 times 1 over x. And the question is, okay, well, what do we do with this 1 over x? Maybe remember this, but notationally, 1 over x is the same as x to the negative 1. And then further on, if we had a different question, 1 over x squared, this would be x to the negative 2, or 1 over x to any power, the nth power, would just be x to the power of negative n. So a general kind of hint, or a kind of trick, I suppose, in some ways, if you have some, let's say, some term, and it's, let's say, 5 over x squared, and you want to write it in an equivalent form where there's no variable in the denominator, you can just keep whatever value is on top, and then just bring up this whole x squared, or whatever it happens to be, but replace the power, that is to say the exponent, just put a negative in front. So if we had, let's say, I don't know, 12 over x cubed, we could bring that up and write 12x to the negative 3, for example. And that would be fine. Okay, and maybe I'll just do one more. Let's say we had 2 over 3x squared, something like this. We can keep this 2/3 times, 2/3 times 1 over x squared, and we know that this would be 2/3 times, well, x to the negative 2. So following along, I'll get a different color, following along on this idea that 1 over x raised to any power just becomes x to the negative of that power. We can use this general structure to rewrite, and we're going to need to rewrite our function before we can take the derivative of it. So let's rewrite this function, and then we can take the derivative. F of x is equal to x squared, x squared minus, and then let's use that strategy. Let's keep this negative 3 here, and let's bring up this x. X used to be raised to the power of 1, and now it's negative 1. Okay, now we have everything we need to take the derivative. That's at f prime. And let's go ahead and use this formula right here. So let's multiply this exponent, this 2 out in front. And then we have 2x, used to be squared, used to be to the power of 2, now it's 1. We don't really need the 1, so let's leave it. And then, following along, we have this -1 power. Let's multiply it out in front. -1 times -3 is going to give us +3. And x used to be raised to the power of -1. Let's take 1 away from that, and now it's going to be x to the -2. And that's our derivative. Okay, that was the first part of this question. The next part, they're telling us there's some line L and it's tangent to f of x at the point 1, -2. Just kind of reminder of what tangent means. Tangent means that if we have some function, let's say like this, and it's at some point right here, if we're looking at a tangent line, we're looking at a line that just touches the function just barely. Essentially, it's the slope of a line at a given point. So that would be one tangent line. If we wanted to find the tangent line here, let's use, be the same color, I suppose. The tangent line would be the slope of the line at a given point. It doesn't need to be positive. It can also be negative and so on. But when we're talking about tangent, we're talking about the slope of a line at a given point. So they're asking us to find a tangent to f of x at this specific point, 1, -2. So how could we possibly do that? So this is exactly what our derivative or our slope function does for us. So this is our derivative, but it's also called the slope function. And what that means is that, like any function, you can put in some value, some input, and it'll generate some output. So here we can replace x with some value, and what the derivative or the slope function will do for us is it'll tell us the slope of the function at that particular point. So for example, if we wanted to find the slope of the function right here, we could put that value into our derivative. Let's say this is x is equal to 3. We put x is equal to 3 into our derivative, our slope function once again, and out would come, who knows, maybe a value of, I don't know, m is equal to 5 or something like that. And let's say we had this other point right here where x is equal to 1. We put in 1 into our slope function, so just put a 1 in here, replace all the x's with 1, and it would maybe give us a value of m, a value of m is equal to -2. And that's what our derivative does for us. It tells us the slope of a line at a given point, or, not to throw too much terminology, the tangent line, the line which just touches a function at one specific point, at that exact point, and it shows you the slope, the rate of increase at that given point. That's our tangent line. So here, they're asking us to find a tangent line at this point 1, -2. Our functions, usually our inputs for our functions, actually always our inputs for our functions, if it's just in terms of f of x, it's just going to be x. So we're really only concerned about this x here. So let's look at our slope function. F prime of x is equal to 2x plus 3x to the -2. And let's input this value of 1. If we input this value of 1 into our slope function, or our derivative, it's going to tell us the slope of a line at that given point. So there we have it. We put in 1 into our derivative, or our slope function, and it'll tell us the slope of a line at that given point. And the slope of a line at a given point is just the tangent line. They mean kind of the same thing. This right here is essentially the tangent, and it's also the slope at a given point. So f prime of 1 is equal to, you can work this out on your calculator, is going to be 5. Not to circle around the point too much, but essentially what we're saying is when x is equal to 1, the slope of this function, or its rate of increase at this specific point, is equal to 5. Okay. Determine the number of lines parallel to L that are tangent to f of x. Justify your answer. So this is kind of like an abstract question. More recent questions are sometimes actually more contextualized, so more real-world situations, but this isn't an impossible question. Determine the number of lines parallel to L, so parallel to this line right here, this L, that are tangent to f of x. Justify your answer. Number of lines parallel to L that are tangent to f of x. So what's going on here, and how can we possibly solve this? What are they actually asking? Let's say we have some function. This isn't the function above. It's not this function in particular, but if we have some function, for example, and let's say it looks like this. I'm going to draw some kind of cubic function. Maybe I'll change it just a little. So let's say we have some function like this. And we've found, let's say, this point when x is equal to 1 and y is equal to -2. So, sorry, let me just change this once more. So x is equal to 1, y is equal to -2. Let's imagine it's right here. 1, -2. And we found the slope of this tangent line. And we said, okay, well, the slope is equal to 5. What they're asking is, okay, well, how many lines are there that are parallel to this L? Right? This is L right here. And the question is, okay, well, how many different points are there on this line that are also going to have, in this case, a slope of 5? How many different points are there on this function where the rate of increase at any given point is equal to 5, where the slope is equal to 5? So how could we do that? So our derivative itself is our slope function, right? And like any function, it accepts inputs, and you put in some input, and then you get some output. So in this case, we put in an input of 1, and the output was 5, which told us that at this point 1, -2 in this case, the slope was equal to 5. So functions accept inputs and outputs. We input some value x, and we get some slope 5. Here, what they're saying is, okay, well, how many points on the line are there, or how many points are there on this function where the slope is equal to 5, where the slope is equal to 5? So in this case, we know our output. We know the slope has to be 5, but the question is, okay, well, how many different x's are there that we can substitute that will make the slope equal to 5? So here, once again, is our slope function. F of x is equal to 2x plus 3x to the -2. And in this case, we don't want to put in an x, an input. We want the slope. We want f prime of x, which is equal to m, right? That's exactly what it is. It's a slope function. We want m to be equal to 5. So essentially, we want f prime of x to be equal to 5. So let's replace this with a 5. And now we have 2x plus 3x to the -2. And not to circle around the point too much again, we're saying, what are the x values? How many different x values are there that we can substitute that will make the slope equal to 5? All right. So in this case, we wouldn't want to end-solve this exactly, because it would just give us one value. End-solve would just give us one value. And we want to know the number of lines that are parallel to L. So in this case, I think we'd be best off graphing it. So let's go to the calculator, put in our derivative. So here is our derivative, 2x plus 3x to the -2. That's our derivative. So at any given point, it tells us the slope. And we want to say, okay, well, how many different values are there? How many times does this slope function equal a value of 5? So let's graph another function. And we know that there are 1, 2, and then 3 different points in which we have a slope of 5. Or we can say 3 different times in which this 2x plus 3x to the -2 is equal to 5. Right. So determine the number of lines parallel to L that are tangent to f of x. Going back to the document here, we could say 3 lines, but we would usually want a little more process. So let's go ahead And if you have a graphical solution, it's best to provide at least a sketch. In this case, just looking at the calculator screen, just a little here, something like this, and then something like this. And we have another line just going through. And then we could search 1, 2, 3 points. That might be enough. I'm actually just going to find those values and place them on this function right here, or on this sketch. Would you need to do this for process marks? I think the sketch itself is actually okay. 6.86, and then this is of course 5. This one right here is 1.5, and this final point right here is 2.19 and 5. I'm tempted to bring up the mark scheme, and to be honest, actually I think I will. Let's have a look at the mark scheme. Just bear with me for 1 sec. Or you can skip ahead, I suppose, of course. Okay, so here it is. Here are our solutions, and here it is. Y is f prime of x, so here's our derivative, and then y is equal to 5. So 1, 2, 3 points. 3 points of intersection marked on the graph, that's answer. And then of course there are 3 lines. So sketch is method, 3 points of intersection is one of the answer marks, and then of course stating 3 lines. Alright. Okay, let's go back to the document then. Okay. Alright, question 2. Irina uses a set of coordinate axes to draw her design of a window. The base of the window is on the x-axis. The upper part of the window is in the form of a quadratic curve, and the sides are vertical lines as shown on the diagram. So here's the base of the window, here's the upper part of the window. The curve has endpoints 0, 10, 8, 10, and its vertex is 4, 12. Okay, so let's look at this. What does vertex mean, first of all? The vertex means a max or min. In this case, it's a maximum, so the highest point. This is our vertex. There's nothing to say that the vertex couldn't be the other way around. If we had something like this, then this would be the vertex. But essentially it's the turning point of, in this case, a quadratic. Of a quadratic, always a quadratic. Okay, so the curve has endpoint 0, 10. That means x is 0 and y is 10. Let's label that. And then 8, 10. So x is 8 and y is 10. So on the same level. This, of course, we know is 0, 0. And we know this vertex right here is 4, 12. And then I guess if we wanted to, we could say that this is 8, 0. Okay. The quadratic curve can be expressed in the form y equals ax squared plus bx plus c, for x is greater than 0, greater than or equal to 0, and less than or equal to 8. Write down the value of c. Okay. So what's going on here is we have this general form of a quadratic. Just like we have the general form of a line, a linear equation is y equals mx plus b, this is the general form of a quadratic. And if we find these missing ingredients, a, b, and c, then we've got a quadratic. Just like if we find m and b, we've got a line. So write down the value of c. Write down the value of c. For an equation of a line, this y equals mx plus b, this is the y-intercept. We plug in x is equal to 0, and then we get the value of y when x is equal to 0. Write down the value of c. In this case, there are a few different ways we can do it. The easiest way would just be to use this point right here, this 0, 10, when x is equal to 0, y is equal to 10, and substitute to find the value of c. Because when we substitute this x is equal to 0, that means let's say this x is equal to 0 and this x is equal to 0, we know that all of these are going to go away. This is going to go to 0, this is going to go to 0, and we're just going to be left with the value of c. So substituting this value of 0, 10, y is equal to 10 when x is equal to 0, plus c, we have 10 is equal to c. Often with these kind of questions, when we're just trying to solve some unknown, we can often put the initial starting value. So x is equal to 0, and then what is our y value at that point? What is our starting value? There's another way to do this actually by, in some sense, actually skipping this value and then going on to the second part of the question and coming back. All right, part 2. Form two equations in terms of a and b. So we want an equation in terms of a and b. So let me erase this just to clear it up again. All right. Okay. So write two equations in terms of a and b. Well, what did they give us? They gave us this set of values, xy values, these set of xy values, and these set of xy values. So to write another equation in terms of a and b, we can just substitute these other 2 points. So 8 and 10, where x is equal to 8 and y is equal to 10. So let's do that. 8, 10, where x is equal to 8 and y is equal to 10. And let's use this equation right here. So we have 10 is equal to a. This is going to be 8 squared plus b times 8 plus, and we know that c is equal to 10. So let's rewrite that actually. 10 is equal to 64a plus 8b plus 10. Let's use the other point as well. 4, 12. So here we have 4 and 12. X is equal to 4, y is equal to 12, and we'll substitute those values in as well. A 4 squared plus b, this is x once again, plus 10. Cleaning this up just a little, 16a plus 4b plus 10. Now we have two separate equations. We have equation 1 here, and then equation 2. All right. Form two equations in terms of a and b. So essentially we have an equation and it's just in terms of these variables a and b. That means we can keep them all by themselves. We just want an equation in terms of a and b. We don't need to solve it, not yet. All right, hence find the equation of the quadratic curve. Okay, so a few different ways you can actually solve this. I'll show you both ways. The way that they're kind of nudging you is they're saying, hey, we have one equation here, and we have one equation here. We have two equations, two unknowns, that is to say just a and b. We can use linear solve to solve this. So two equations, two unknowns, lin solve, and that should give us the answer. Often that's the kind of structure when they ask you to write equations in terms of a and b, two equations, two unknowns, three equations, three unknowns. We can put it into lin solve. So let's go ahead and do that. So go into the calculator screen. Let's go menu, algebra, and let's go solve system of linear equations. We have two equations. They're in terms of a and b, so let's actually just write that. You can use x and y, but it just makes it easier. And let's input those equations. 2, 64a plus 8b plus 10. Oops. And we have 12 equals 16a plus 4b plus 10. And that should give us our values. So since this is a and this is b, we know that a is equal to negative 1/8 or negative 1 over 8, and b is equal to 1. So let's go and write that out in the document. So just returning You know, a is equal to negative 1 over 8, b is equal to 1, and our quadratic curve was in the form of y equals ax squared plus bx plus c. So all the way up here they gave us the form of the quadratic, and they said, hey, find a, b, and c. C was equal to 10, so c is equal to 10. Now we can find the equation of the quadratic curve. It's y is equal to negative 1 over 8 x squared plus 1 times x, or just x, plus 10. Alright, not too bad. Let's go back to the calculator screen just for a sec. I'm going to clear a new window. I think there's actually an easier way to work this out. And they're kind of nudging you to solve it through a system of linear equations. But the other way to work this out is just to set x, y values and then just put the coordinate points that they gave us. So if you remember, they gave us 0, 10, and then they gave us 8, 10, and 4, 12. And just like if we have 2 points on a line, we can write an equation of a line. 3 points allows us to write the equation of a quadratic. So 2 points, linear regression. 3 points, we can write quadratic regression. Let's go statistics, stat calculations. We don't want a linear regression, we want a quadratic regression. X is replaced in the x, the y coordinates, the y were in the y. There we go. And there's our a, b, and c once again. A is equal to negative 1/8, just in decimal form. B is equal to 1, and c is equal to 10. And it actually gives us our general form of a quadratic as well. This ax squared plus bx plus c. And it tells us those values of a, b, and c. So, another kind of method available. They're pushing you, or kind of nudging you. Actually, they're telling you in some ways to solve this through a system of linear equations, but 3 points, and we can write our quadratic. We can find those values of a, b, and c as well. Okay, let's go back to the document and continue on. Alright, find the area of the shaded region in Irina's design. Okay, so we want to find this, essentially, the area under the curve. So we want to find the area that is under this curve right here. What do we know? We know that this quadratic can be expressed, so this line, or at least this part of it between 0 and 8, can be expressed through this, this negative 1 over 8 x squared plus x plus 10. And we want to find the area that is under this curve between the values of 0 and 8. So it starts at 0 and end at 8. You might remember, area under a curve is given by our integral, or the sum. So in this case, let's go back to the formula booklet. Formula booklet will tell us the area of a region enclosed by a curve. The area is equal to, and this capital, this Greek S, is the sum of the area under the curve, where A is our starting point, B is our endpoint, and then Y is just the function, and then of course X is just its in terms of X. So we have a starting point, ending point, and then we have our function. So let's go back to the document and work this out. So here it is. The area under the curve with starting point A, ending point B of some function, f of x or y. We have it expressed in this form, where this is our area. And so in this case, we want to find the area under the curve with a starting point of 0 right here and an ending point of 8. So starting point of 0, ending point of 8, and then once again our function was negative 1 over 8 x squared plus x plus 10, and it was in terms of dx. These will always match. Whatever this is, then so is this. The IB exam will only ever give you x's. Okay, let's go back to the calculator and work this out. Menu, calculus, and we want to find the numerical integral. There we go. That's exactly what we have here. Starting point, ending point, and then our function negative, let's put 1/8, negative 1/8 x squared plus x plus 10, and then it's in terms of dx. Remember, these match. Here we go, 90.6667 or 90.7. So let's go back to the document and work it out. So there we are, 90.7, the area of the shaded region. To be honest, if you're comfortable with the structure, that could potentially be one of the easiest questions on the test, at least potentially. Nice kind of 3 marks. All right, let's go on. 8-mark question from 2021. Okay, this is a tough question. I think it probably occurred near the end of an exam. Let's have a read, see what we can do. Xion hits golf balls into the air. Each time she hits a ball, she records theta, the angle at which the ball is launched into the air, and L, the horizontal distance in meters which the ball travels from the point of contact to the first time it lands. The diagram below represents this information. Okay, so here she is. She's hitting the ball at 75 degrees, and we see how far it goes. At 60-degree angle, and we see how far it goes, and so on, so on, so on. She analyzes her results and concludes that, this is going to look kind of wild and crazy, I suppose, that the change in the length by the change in theta is equal to negative 0.2 theta plus 9. And then this right here, remember this is the angle. She's only experimenting between 35-degree angles, so something like this, and 75. So she's not like hitting at 90-degree angle or just along the ground, I suppose. Okay, so what does that mean? It gives us the change in theta and the change in length. So as we alter the value of theta, to what extent are we altering the value of the length? Kind of abstract, but I don't actually think they're asking us to do too much with this, I suppose, at least at the moment. So part A asks us to determine whether the graph of L against theta is increasing or decreasing at theta is equal to 50. So the graph of L against theta, this is change in length over change in theta. So we don't actually know the graph of L and theta, change in L over change in theta, but we do have the slope function, right? This is our gradient or our slope function because it's a derivative. We often see our derivative expressed as dy dx, which is the same as f of x, but here they're using L and theta, so two different variables. Kind of an unusual question, but really we can take any variables we want. We don't need it just in terms of y and x. In this case it's L and theta. I just said above that they wouldn't ask you to integrate using any other variable besides x, and I haven't seen one, but potentially it's possible, I suppose, looking at this one. Okay. Wait until that passes. Okay. Determine whether the graph of L against theta is increasing or decreasing at theta is equal to 50. So we've got some function right here, and if we wanted to, we could write it as, it's a little unorthodox, but we could write it as f prime of L. Actually, no, f prime of theta, rather. F prime of theta is equal to negative 0.2 theta plus 9. And if we put in a value of f prime of 50, for example, that is to say when theta is equal to 50, we can ask whether the slope is positive or negative. So is it increasing or decreasing. So negative 0.250 plus 9. What would this be? This would be negative 10 plus 9, or negative 1. And what that means is at this specific point, the slope is equal to negative 1. And if the slope is equal to negative 1, it means it's going down, and then we therefore have decreasing. So whether the graph of L against theta is increasing or decreasing at theta is equal to 50, let's input a value of theta for 50, or 50 for theta, and then find out what the slope is. So just looking at this right here, this L against theta, this might be something like this. If this is our graph, for example, maybe we have, I often draw it like this. I will again, I guess. But if we have something like this, and if this is, let's say, a value of 50, right here, what does that mean? That means the slope at this given point, wherever it is, when theta is equal to 50, that m is equal to negative 1. At this particular point, the graph of L against theta is negative when theta is equal to 50. Okay. Moving on. Sien observes that when the angle is 40 degrees, the ball will travel a horizontal distance of 205.5 meters. Find an expression for L theta, or L of theta. Kind of a good question. You see it's 5 marks. Often these kind of questions follow a similar structure, and if you've seen a few of them, you might already recognize. Here they give us the derivative, that is to say the change in L over change in theta, and then they give us a point on the actual function, and they say we don't want change in L over change in theta, or change in y over change in x. We just want the original function. So if they gave us this, they gave us f prime of theta, which here is expressed as dl over d theta, and it was negative 0.2 theta, 0.2 theta plus 9. And they're saying, okay, we don't want f prime of theta, we just want f of theta, or in this case, L of theta, rather. So we don't want L of theta, L prime of theta, we just want L of theta. Okay. So essentially, we have the derivative, but we want the original function. In that case, we would take the antiderivative. All right, what makes this a difficult question, I think, is that the variables are switched around. Here we're using L and theta, and it's much more common to use dy dx. Since we're using dl d theta, we see that this theta is the same as this theta, just like dx would be the same as some function written in terms of, I don't know, let's say x. Our original function, actually, I think it was like x plus 3x to the negative 2. We see these match up, just like these match up. They're using different variables, but essentially the process is the same. So let's work it out. I'm going to erase this. Okay. So let's take the antiderivative. Antiderivative, this is also given in the formula booklet. If we have some function, some function f of x, or f prime of x, and it equals to x to the power of n, and we want to reverse the process and find the original, what we would do is we would, in this case, add 1 to the exponent, but also divide the whole function by whatever that new exponent is. So let's work this out right here. L theta. L theta is equal to, let's keep this negative 0.2 theta, but it used to be theta to the power of 1, now it's going to be to the power of 2, and let's divide out by that new value. plus 9. We know if there's a constant and we take the derivative, just some variable x, and we take the derivative, the x itself would go away. So if we want to take the antiderivative, this would be not 9x, but 9 theta. And constants, if they exist, would just disappear. Why is it 5? No, it's c. If you want to check out to see whether you've done the antiderivative correctly, you can always just reverse it. Here we see the constant goes away, 9 theta just goes to 9, and then of course multiplying out by 2, this would be negative 0.4 over 2, which would take us back to this negative 0.2. Alright, let's actually clean this up just a little. L is equal to theta equals, and this is going to be negative 0.1 theta squared plus 9 theta plus c. Would you need to clean it up like that? Probably not. Well, potentially actually. It's always not a bad idea if you can. Just go into the calculator and divide this out and you'll get a simplified decimal. Okay, 5-mark question, not quite done yet. We want to find the value of c, this unknown constant. They give us an theta value and they give us the length. So this is essentially inputs, outputs. Usually we call this our x and this our y, but now this is essentially equivalently our theta and this is our L. So let's substitute those in. The length we know is 205.5 meters when theta itself is equal to 40. So let's put that in, 40 squared plus 9 times 40. And now we just have c to solve for. I'm going to go to the calculator really quick. And actually I'm going to use the calculator that I have beside me right here. 40 squared times negative 0.1 plus 9 times 40. And then let's take that away. 205.5 minus, and we get a value of c is equal to 5.5. If you wanted to work this out, of course you could just end solve for c, and that would be fine as well. Here at c is equal to 5.5. So completed expression, L of theta is equal to negative 0.1 theta squared plus 9 theta plus 5.5. Alright, kind of a wild question in some kind of way. Kind of rare. It's almost certainly a kind of final question where they're asking you to deal with variables other than x and y. We're talking about L and theta and so. Alright, let's move on. Question 4. A company produces and sells electric cars. The company's profit, P, in thousands of dollars changes based on the number of cars, X, they produce per month. The rate of change of their profit from producing X electric cars is modeled by change in profit over X is equal to negative 1.6x plus 48. Okay, so the rate of change of their profit. Remember, anytime you see a derivative, it's the rate of change. It's the slope of a line at a given point. It's the rate of increase or the rate of decrease. Alright. This is actually really similar to what we had before. The company makes a profit, so P, of $260. P is equal to 260 here. When they produce 15 electric cars. So X is equal to 15. And then once again we have dP over dx. But we don't want dP over dx, we just want P of x. So we want to move from a derivative to the actual function. And to do that, we would take the running out of space, the antiderivative. So here it is. Here's our derivative, 1.6x plus 48. This one's actually a fair bit easier compared to the last one. Let's write out negative 1.6x. X used to be 1. Let's add 1 to it. Now it's squared. Let's divide out by that exponent. Plus 48. If we would take the derivative of this and get back to here, we would know that this 48 once had an x and then we had some unknown constant c. All right, let's substitute those values. P is equal to 260. Our profit is $260,000 when they sell, what is it, 15 electric cars? 15 electric cars over 2 plus 48, and then we have 15 electric cars plus c. This time I'll actually go ahead and end solve it as well. So let's go ahead and do that. Going to the calculator screen. That's, algebra, numerical solve. 260 equals, set this up, negative 1.6, and then we'll have 15 squared all over 2 plus 48 times 15 plus c, and we want to solve for c. Alright, there it is. Okay, so sometimes actually when you put those brackets right beside another value, if it's brackets beside a variable, then sometimes the calculator won't work and you might actually need to put a multiplication symbol. But in this case, if it's just values being multiplied by values, you're okay. And so c is equal to negative 280. Is that correct? Let's see, 260, produce 15 electric cars, 15. Looks good. Okay, so let's go back to the document. C is equal to negative 280, so the whole function itself. P of x is equal to this negative 1.6 divided by 2. If you put that onto the calculator, you'll get negative 0.8. And so I'm just going to clean it up a little. X squared plus 48x minus 280. Okay, there we go. The company regularly increases the number of cars it produces. Describe how their profit changes if they increase their production to over 30 cars per month and up to 30 cars per month. Justify your answer. Okay. How does the profit change? Oops. How does the profit change? So here we have a function that tells us the profit for different values of x. I think a good strategy here would be to put in values of x for when x is equal to 30 and x is equal to 50 and c. So actually even better, let's just graph this function and see how the profit changes. So let's go to the calculator and graph this function. So negative 0.8 x squared plus 48x minus 280. Alright, let's zoom fit. Hopefully that will be enough. Okay, not great. Let's zoom a little more. Okay, that's workable. Okay, let's use graph trace and find those values when x is equal to 30. Okay, when x is equal to 30, we have a profit of 440. And let's use graph trace again. And let's put in a value of 50. Actually, we can see that when x is equal to 30, we're at 480. And then our profit actually just decreases. So let's go back to the document for a sec. And what did we have? We had when x was equal to 30. How can we do this? We can write the profit from 30 cars, and then we worked that out, and it was equal to 480. And the profit from 50 cars was equal to 120. And this would be enough to say that profit is decreasing. If we wanted to, and I guess if you took the trouble to sketch it or to provide a graph, we could provide a sketch and then label the points as well. 30, 480, which is actually our vertex, it looks like, and then 50, 120. 30 cars make $480, $480,000 in profit. 50 cars, and it actually looks like we start to lose money. All right. So the profit is decreasing in this case. Actually, sorry, I think this was 440. This was for 440. Let me change that here as well. All right. Okay. Let's go on to question 5. Giles charges a customer per hour to hire his boat. It is known that change in profit over change in time is equal to 20 minus 980 over t squared, where t is greater than 0 or less than or equal to 12. P is the cost per hour, or in Norwegian krone, that the customer is charged, and t is the time in hours spent on the boat. The cost per hour has a local minimum when the boat is hired for h hours. So there's a local minimum when the boat is hired for h hours. We're probably going to need to make use of that. So first off, they ask us to find the value of h. So find the value of h. So t is the time in hours spent on the boat. We know that the cost per hour has a local minimum when the boat is hired for h hours. So for some number of hours that we rent the boat, the cost per hour has a minimum. Okay, so what does that mean? If we look at a function itself, and let's say this is p, the cost per hour, and this is t, the time in which we rent, and there's some kind of local minimum. So what does that mean? Not necessarily the minimum of the function itself, but a local minimum. That is to say, the minimum over a given section of the graph, or it reaches a minimum within a certain range. And if it reaches a minimum, just like when we have a maximum, so I'm going to draw a maximum right here, we go through some function and we increase, and then we start to decrease, but after we have done all of our increasing that we're going to do, we're going to have reached a maximum, and the point at which we move from increasing to decreasing, that's going to be a maximum. Similarly, if we're decreasing, and we've done all the decreasing that we're going to do, the point at which we move from decreasing to increasing is going to be a minimum. And here, at both of these situations, whether we have a local max or a local min, that's going to be the point where m is equal to 0, where the slope is equal to 0, where we move from decreasing to increasing. So in this case, they give us the slope function, right, the derivative. And in this case, if we set our derivative equal to 0, we should be able to find that local minimum. That's what they're telling us. Cost per hour, here it is, cost per hour for some given time has a local minimum when the boat is hired for h hours. So we're looking for this point right here, the point at which it has a local minimum, when m is equal to 0. So we have the slope is equal to 0, 20 minus 980 over t squared. And I think that should be good. In this case, what we might want to do, since this is over t squared and t is raised to the power of 2, instead of n solving, we might want to graph this. So let's go ahead and do that. So here we go. Let's have 20 minus, set up a fraction, 980 over, in this case, x squared, and a local minimum. So if we were to n solve, it might give us a negative value or a positive. I think it would actually give us a positive. We know we can't rent the boat for negative hours, so it's just be this positive value here. So let's work it out and find the 0. It occurs when t is equal to 7. So we rent this boat for 7 hours, and that's going to be, I guess, the cheapest cost per hour for us. That's when the slope is equal to 0. Okay. Let's go back to our document then. So t is equal to 0. All right. Sandra hired Gil's boat for 5 hours and was charged 328. 5 hours, 328. Yvonne hires Gil's boat for 7 hours. Show that the cost per hour for Yvonne is 312. And this is actually the third question in a row, so I'm actually going to kind of blaze through this one, I suppose. Essentially what we want to do, we have change in cost over change in time. I think this is given by t. And this is equal to 20 minus 980 over t squared. And essentially what they want us to do is they want us to find, well, just profit as cost per hour as a function of time. So again, we want to take the antiderivative. Let's go through it. Actually, maybe there is something kind of new in this, and that is this variable in the denominator, which is going to complicate things. So let's make that first step and rewrite this. So writing dp over dt, we have 20 minus, and let's write 980, bring up that t, and it used to be t squared, now it's t to the negative 2. Let's use that strategy. Alright, now let's find p, cost as a function of time. 20 all alone, that means it used to have a t, and we have, okay, this is going to be kind of tricky. What do we know? We know that if we have f prime of x and it's equal to x to the n, and if we suddenly want to find how it was originally, we want to increase the exponent by 1 and then divide out by whatever that value is. So let's write negative 980 t, and let's write negative 2 plus 1. So this is going to be negative 1, and then we're also going to divide out by whatever that value is, right? These same value, increase the exponent by 1, divide out by that value. We also know that our antiderivative, potentially, the original function might have had a constant. Let's clean this up. pt 20t minus over minus, so negative 980 over minus 1. This is going to give us a positive. You can work this out. You can always put this into your calculator. Negative 980, you can put that into your calculator. Essentially everything but the variable, and it'll help you clean it up. So this is going to be plus 980t to the negative 1 plus c. They give us a value. They give us t is equal to 5 and p is equal to 328. So let's put those values in. P is equal to 328. 328 when t is equal to 5. 980, this is going to be 5 to the negative 1 plus c, and what we want to do is, once again, and solve for c. I'm going to do that on the calculator. Alright, menu, algebra, numerical solve. 328 equals 20 times 5 plus 980 times 5 to the negative 1 plus c, and then we'll put as a calculator to solve for c. Alright, and there it is, 32. Let's go back to the document and write that out. C is equal to 32. So, writing this function with a new value of c, we have the cost as a function of time is equal to 20t minus 980. Oops, let's use this one right here, actually, that's better. 980t to the negative 1 plus 32. The last part of this question, they wanted us to show that the cost per hour for Yvonne was 312. And Yvonne rented this boat for 7 hours. So let's input 7 here. P7 is equal to 20 times 7 minus 980, 7 to the negative 1 plus 32. And I'm actually just going to go to the calculator. I'm going to work this out. Sorry about my calculator that I have on my side. 980 divided by 7 plus 140. Okay. So, my mistake. This is a plus here, and I wrote a negative. There we go. And so now, this should equal 312. This is 140 plus 140. 140 plus 140 is 280 plus 312. Plus 32 is 312. Okay. Not a bad question, I guess. Okay, moving on. Linda owns a field represented by the shaded region R. The plan view of the field, I think that should be the plane, potentially. The plan view of the field is shown in the following diagram, where both axes represent distance and are measured in meters. Okay. So this is a kind of flat view, as if you were in a helicopter looking down at the field. The segments AB, CD, and AD respectively represent the western, eastern, and southern boundaries. So this is west, this is the east, and this is the southern boundary. The function f of x models the northern boundary, so this function right here, models the northern boundary of the field between points B and C. So here it is, this curved line can be represented by this function right here, and it's between the values of 0 and 70, so 0 to 70. Find f prime of x. Okay, we can do that. So I'm going to rewrite f of x. It's negative x squared over 50 plus 2x plus 30. F prime of x. Let's grab the exponent, multiply out in front. That means this is going to be negative 2x decreased by 1. There's just a 1 there now. Over 50. This is just going to be 2, and then this constant would fall away. If we wanted to clean this up a little, we could write this as negative x over 25 plus 2. So once again, you can just take negative 2 over 50 and then convert that to a fraction if you want. You can write that as a decimal even if you want. 0.04, I suppose. Okay. There's our derivative. Hence, find the coordinates of the field that is furthest north. And this is a great question. So the coordinate of the field that's furthest north. Essentially, they give you the function, and so you could just find the vertex, essentially, the maximum. But what we know is that when we've reached a maximum, we have a slope of 0. M is equal to 0. And what does that mean? That means that f prime of x, our slope function, is also going to be equal to 0. And I think that's what they're really asking you to do. So if we know that f prime of x is equal to, oops, that's a little messy, negative x over 25 plus 2, what is the point when f prime of x is equal to 0? So let's put in 0. Let's ask, okay, well, what value of x is this slope equal to 0? And then we can, of course, end solve. Okay. I'm going to work that out on the calculator. Algebra numerical solve. 0 equals, and then let's set this up. Negative x over 25 plus 2. Okay, 2 for your arguments, right? We need to ask the calculator to solve for x. There it is. X is equal to 50. Okay. Let's go back to the document. X is x is equal to 50. And that looks about right. If we imagine that this is x is equal to 50. Okay, the coordinates. So 3-mark question, they're asking for coordinate points. X is equal to 50. How can we find the y value? Well, just by substituting 50 into here. To be honest, I'm wondering, This hence, the hence indicates that they're asking you to use previous information here. They're asking you to use the derivative. And I'll bring up the mark scheme. Actually, I will bring up the mark scheme. Let's have a look. So this is Giles. They're asking you to use this derivative equal to 0, and then substituting 0, and then finding that value of x. So here they're saying method is 0, answer is 0, you just get 1 for the coordinates. So if you're just graphing the function itself, finding the max that way, you get 1 out of 3. But this hence is essentially saying make use of this previous derivative that we found. Okay, so let's go back to the document again. So we know x is equal to 50, and substituting 50 in to this function right here, f of 50. F of 50 is equal to negative, geez, I think it was negative 50 squared over 50. 50 squared over 50. And then it's plus 2x plus 30. So plus 2 times 50 plus 30. And this would give us the y value. In this case, just working this out, this would be negative 50 plus, oops, this is 2 times 50, plus 100 plus 30 would give us a value of 80. And so y would equal 80 at this point. So I guess maybe kind of key takeaway is this hence is they're saying make use of that previous information. Or your previous findings, rather. Alright. Further on. Point A has coordinates 0, 0. Point B has coordinates 0, 30. Point C has coordinates 7, 72. And point D has coordinates 70, 0. Write down the integral which can be used to find the area of the shaded region R. Okay. Shaded region R. That doesn't seem too bad. So this is our shaded region of R. Here's our starting point. Here's our ending point. We know that this was 70, starting point of 0 to 70. And this was our function. So this actually is not too bad of a question. So a b of some function, whoops, let me rewrite that. A b of some function f of x dx. In this case, our starting point was 0, and we went all the way up to 70. And our function was negative x squared over 50 plus 2x plus 30. And then, of course, it's in terms of dx. But let's go to the calculator, look that up. Calculus, numerical integral at point. Sorry, that's not it. Calculus, numerical integral. Okay, there we are. Starting point, ending point. This is our function. Negative x squared over 50 plus 2x plus 30, and in terms of dx. There we go. Alright, so pretty large farmer's field, I guess. 4,713.33. Let's go back to the document. We know that this is equal to 4,713.33. To 3 sig figs, this would actually be 4710, right? 1, 2, 3. Okay. Find the area of Linda's field. Okay, wow. So this is actually just asking to write down the integral, which would be this section here. That's our integral. And then the area is actually just down here. So kind of a big 4-mark question for, again, if you're familiar with the process, area under the curve, starting point, ending point, function itself, keep these x's or whatever variable it is in terms of one another. So if it's x, we put dx and so on. This is a numerical integral. Potentially, if you're familiar with the process, could be quite good. Okay. Linda used the trapezoidal rule with 10 intervals to estimate the area. This calculation underestimated the area by 11.4 meters. Calculate the percentage error in Linda's estimate. Okay, this is an interesting question. So she used the trapezoid rule with 10 intervals to estimate the area. This calculation underestimated the area by 11.4 meters. Calculate the percentage error in Linda's estimate. So it doesn't seem all that bad, but the question that I'm wondering is, what kind of accuracy are they asking for? Do we use 3 sig figs, or shall we use as much accuracy as possible and just use this 11.4? Actually, I'm just going to look at the mark scheme here. Here's the mark scheme. It looks like what they're asking us to do, so estimate over exact. They're asking the exact to be 4713.33333, so not to 3 sig figs. Actually, sorry, just further down, there is the acceptance of 4710 is used, so they will accept either. If we want to use the exact and put a number of decimal points, or if we want to use the value of 3 sig figs. I think it makes more sense to use the exact, but it looks nice to know that they're accepting both. Okay, so let's go back to the document here. Alright, so percentage error. Percentage error is given by, I'm going to write it out, percentage error is equal to, oops, this is quite messy, estimate minus exact over exact, and of course we want this as a percentage, so we want to multiply by 100%. These are absolute values, which means no negatives, right? Okay, so estimate was underestimated. We underestimated it by 11. Where was it? Find the area of Linda's field. That seems a little funny. Sorry. Let me just take this and put it in its right place. Okay. Calculate the percentage error. So Linda underestimated by 11.4. So compared to the exact, estimate minus exact, she's 11.4 off. So what we can do is we can say that this estimate minus exact is going to be 11.4. Essentially it's the same as saying 47133 minus, and then if we were to take 11 away from this, and then this would be, what would it be? It would be 4, 7, for example, 1, 2, 3, 3, 3, 3, 3, so on. Actually, no, it's 11.4, so a little different. But essentially, the difference between estimate and exact is 11.4. Above or below, we don't know. So it's best to just write difference is 11.4. And the exact is 4713.33. We can put more 3's and so on, times 100%. Okay, let's go to the calculator and work this out. I'm actually going to work it out in parts. 11.4 divided by 4713.33, and so on. And then we'll multiply this by 100. And so this is our positive percentage. Remember, if you work this out and you get a negative, percentage error says no negatives allowed. That's why we have the absolute value sign. So no negatives. So here we have 0.242% after we multiply it by 100. So let's go back to the document. 0.2418 or 2.42%. All right. Suggest how Linda might be able to reduce the error while still using the trapezoid rule. Can reduce the error by increasing the number of intervals. So if you take some function, just really quick to kind of give you a demonstration of how, let's say we have just a plain quadratic. If we just have two intervals, right? Oops, get rid of that. We just have two intervals, we have something like this, right? But if we want to, let's say, have three intervals. Oops. There we go. If let's say we have 1, 2, 3, or 4 intervals, then now we improve on the error because we get closer to the curve. So with 3 intervals, or 4 intervals, and so the more intervals we have, the more accurate we'll be. So how she might reduce the error, she can use a greater number, or more essentially, greater number of intervals. Alright, let's look through this. Question number 7. The function f is defined by f of x equals 2 over x plus 3x squared minus 3, where x does not equal 0. Find f prime of x. Okay, we've done similar ones, so I'm actually just going to kind of go through this one a little quick. So f of x is equal to 2 over x plus 3x squared minus 3. Let's rewrite this. Let's bring the x up, x to the negative 1 plus 3x squared minus 3. Taking the derivative, multiplying out in front, this is going to become negative 2x, decreasing by 1. Let's multiply out in front, 6x, decrease by 1, and then the constant goes away. So there's our derivative. Potentially, I mean, if you get used to the process, like, you can really make some good time up here. Of course, make sure to take your time. Variable in the denominator, make sure your steps are all correct, but often you see a lot of calculus questions do give you a function to say, state the derivative. Alright. Find the equation of the normal to the curve y equals f of x at 1, 2 in the form ax plus by plus d. 4-mark question. Kind of a light number of marks. I think this is quite a few steps involved. Where a, b, and d are elements of the integers. This means positive, negative, whole numbers. That's what that z means. It comes from the German Zahlen, so counting numbers. Positive, negative, whole numbers. I guess not exactly counting because they're negative, but positive, negative, whole numbers. This is what this this integer value means. Okay, how can we do this, and what is it asking us? So, the normal to a curve is this. Essentially, the point that is perpendicular to some function. I'm going to draw the same function again, y and x, some function that goes up and down, and if we want to find the normal to the curve at this point, let's say 1, 2, right here, in this case we don't want the tangent, we want the line that is perpendicular to that tangent line. That's what the normal is. This is the normal, and this right here is a tangent line. So we want the normal in this case. So let's see what we can do. I'm going to kind of just describe what's going on, I suppose. So here's our derivative. This is our slope function. And we saw earlier that if we substitute some value of x or as an input into our slope function, it gives us the slope at a point. So let's do that. F prime of 1 when x is equal to 1. That's our input. What is our slope of the line at that given point? So, whoops, let me just put in a value of 1 here. Negative 2 plus 6 to the 1. You can work that out on your calculator. This one is actually just going to be negative 2 plus 6, or it's just going to be equal to 8. Or, sorry, going to be equal to 4. I'm actually going to write this out because I think I'm going to need some space here. Okay, so negative 2 plus 6, this is going to give us a value of 4. So what do we know? We know that, for example, this is not how the function looks, but we can imagine that m is equal to 4 at this point. And so what is the slope of the perpendicular? So if m is equal to 4, we know that m perpendicular, 4 over 1, switch the top and the bottom, m perpendicular would be negative 1 over 4. So switch the top and the bottom multiplied by a negative. Perpendicular would be negative 1 over 4. So if our equation of a line is in the form of y is equal to mx plus b, we know that our m is negative 1 over 4x plus b. Now the question is, what is b? We have a point on the line. We have an xy value, so let's substitute that in. X is equal to 1 when y is equal to 2. So let's put 2 in for y. Negative 1 over 4, x is equal to 1 plus b. We can end solve this. I'm actually just going to work it out. And this is going to be 2 1/4. Or what could we say? We could say that b is equal to, we could say this essentially. We could say it's 2.25, or we could say it's equal to 9 over 4. I'm actually just going to go to the calculator really quick to show you something. So we can work this out and we can convert decimals. So if we were to, let's say, let's go algebra, and we were to end solve this, and we were to say 2 is equal to, and we were to end solve that original situation, negative 1 over 4 times 1 plus b, and then ask to solve for b, and it would give us 2.25. We can go menu, number, and then approximate to fraction. And then it would give us that 9 over 4. And sometimes it's going to be a lot more useful, potentially at times. It's going to be easier to convert fractions to whole numbers than potentially decimals. Maybe. Okay, so let's go back to the document for a sec. So b is equal to 9/4. Now we have the equation of the normal line. It's y is equal to negative 1 over 4x plus 9 over 4. And what this is saying right here, this ax plus by plus d is equal to 0, they're saying, hey, we don't want anything on one side, we just want everything on one side, and this a, b, and d, this a, b, and d can only be positive, negative whole numbers. So let's bring everything to one side. Y is already on this side, but let's bring this x over, this negative 1/4 x. We bring something from one side to another, it changes signs. So it's negative 1/4 x becomes positive 1/4 x. This y was already here, and then let's bring this 9/4 over. It was a positive 9/4, and so now it's going to be negative 9/4 is equal to 0. We don't want fourths, we don't want quarters of a number or 9/4, we just want whole numbers. So if, for example, we have a quarter of something, let's say we have a quarter of an x, which I suppose we do, we want a whole x. And so this represents 1/4 of an x, but we don't want a fourth of an x, we want a whole one. So we need to take this, we need to multiply by 4. Let's multiply everything by 4. We can't just multiply one thing by 4 because we upset the balance. If these things are really equal to one another, what we do to one side, we have to do to the other, and we have to make sure we do everything equally as well. So 1/4, let's multiply this by 4, multiply this by 4, and multiply this by 4. So 1/4 x times 4 is just x, y times 4 is 4y, and negative 9 over 4 times 4 is equal to negative 9. And there we go. And that would be our equation. X plus 4y minus 9 is equal to 0. All right. Okay, let's keep going. A company's profit per year was found to be changing at a rate of dp dt. Is this, did we do this one yet? No, I suppose not. Company's profit per year was found to be changing at a rate of change in profit over change in time is equal to 3t squared minus 8t, where p is the company's profit in thousands of dollars and t is the time since the company was founded, measured in years. Determine whether the profit is increasing or decreasing when t is equal to 2. Okay, so once again, this is our derivative or our slope function. It tells us the rate of change at a given point. So whether the function is increasing or decreasing, going up or going down at a given point. What we should be able to do is we should be able to substitute t is equal to 2, or 2 for wherever we see a t, and we'll see whether we have a positive or negative value. If we have positive, that means it's going up, it's increasing, and if it's negative, then we have a negative slope and it's decreasing. So let's substitute t into here. So dp over dt, where t is equal to 2, 2 squared minus 8 times 2. This is going to be for 12 minus 16, which is going to be negative 4. So change in profit over change in time is equal to negative 4. Slope, essentially this is m, right? Slope is equal to negative 4, which means that this is, it's decreasing at a given point. Alright, 1 year after the company was founded, the profit was $4,000. Find an expression for PT. Okay, so again, they're giving us 2 points. 1 year, that is to say when t is equal to 1, profit was 4. They're giving us 2 points and they're saying, hey, we've given you the derivative, can you find the original function? Okay, so let's write it out. dp over dt, this is our derivative, was 3t squared minus 8t. Alright, 3t squared minus 8t, and just make sure, good. Let's find p. Alright, let's take 3t, increase the exponent by 1, divide out by that new value, minus 8, increase the exponent by 1, used to be the power of 1. Let's divide out by that new value, and potentially we might have had a constant initially. Let's clean this up. 3 over 3 is just going to be 1, so we'll have t cubed. Whoops. Minus 8 over 2 is going to be 4t squared plus c. They also give us a value of p is equal to 4 and t is equal to 1. So let's input those values. 4 is equal to, t is equal to 1, 4, 1 squared plus c, and now we can end solve for c. Okay, I'm actually just going to work that out. I'm just going to work it out. 4 is equal to 1 minus 4 plus c, and that means that c is equal to 7. Okay, so let's write out our whole function. P is equal to t cubed minus 4t squared plus, and then we found the value of c is equal to 7. Okay, I think that's good. All right. Oh, trapezoid rule. I think I might actually skip this one, to be honest, because we've done a lot of trapezoid rules. Maybe we'll do this. Interval 0.4, estimate the total amount of carbon dioxide. Real amount of carbon dioxide. Find the percentage error. Classic question. 3 marks seems a little light. But I think we've done a lot of trapezoid rules, so I think I'm actually gonna skip this one for now. Let's see. Let R be the rate in tons per hour. Yeah, for this one, I think it's a kind of more straightforward kind of trapezoid rule question. Should we do it? Let's have a look. If you want, you can, of course, skip ahead. So here's our trapezoid rule right down here. It's an estimate for the area under the curve. So h, remember, ending point minus starting point divided by number of intervals. and then starting value, ending value, just count once, and then 2 times all of those intermediate values. So potentially we could do it. Okay, so use the trapezoid rule with an interval of 0.4. Okay, so if we're going from 0 to 2, we're finding an estimate for the area under the curve of this function from 0 to 2 of some function f of x. And we know it's going to be 1/2 h. H is equal to b minus a over n number of intervals. So interval is 0.4. So how many intervals do we have? How many trapezoids? Well, we'd go from 0 to 4. That would be 1, 2, 3, 4. We would have 5 trapezoids. So essentially, if we end at 2 and we started at 0 and we go by, or we break it up into 5 intervals, 2 divided by 5 gives us an interval width of 0.4. So actually, it kind of gave it to us already. So h is equal to 0.4. And now let's set this up by looking at the starting value of 30. Whoops. That's okay. 30 plus ending value of 50 plus 2 times all of these intermediate values. So 50 plus 60 plus 40 plus 20. All right. I think that's it. So actually, one thing, this should be an estimate because that's what our trapezoid rule is. I'm going to work it out on my calculator right here. 50 plus 60 plus 40 plus 20 times 2 plus 80, and then times 0.5 times 0.4. Okay, I'm getting a value of 84. Okay, real amount of carbon dioxide emitted during these 2 hours was 72 tons. Find the percentage error. Percentage error, remember, is estimate minus exact divided by exact. So this is the real amount. And then we want to multiply by 100. I'm going to work it out just real quick, not exactly cutting corners, but skipping some explanation. So estimate minus exact over exact, and then times 100%. So remember, whatever this comes out to, if we were to have reversed it, this is an important part. If we, for example, had 72 minus 84, giving us a negative value, we want this always to be just a positive value. So divided by 72 times 100, this would give us 16.7%. Always a positive difference. Okay. Good. Number 10. The surface area of an open box with a volume of 32 centimeters and a square base with side lengths x centimeters is given by s of x is equal to x squared plus 128 over x, where x is greater than 0. Find s prime of x. Okay. Similar procedure, once again, let's write out our original function. X squared plus 128 over x. First, if we want to modify this, we're going to need to modify this because we have a variable in the denominator. Let's write x squared plus 128. Bring up the x. Now it's x to the negative 1. Now we can take the derivative of this s prime. It's going to be 2x. X used to be 2, now it's 1. Let's multiply this negative 1 out in front. This is going to be negative 128x. X used to be negative 1. Take away another 1. Now it's negative 2. That's our derivative. Solve s prime of x is equal to 0. Okay, so s prime of x is equal to 0. Let's set this equal to 0. So wherever we see an s prime of x, let's set it equal to 0. X to the negative 2. Essentially, we're actually saying, okay, what are the values of x where this is equal to 0? We could end solve this, and there's only 2 marks, So it looks like this would be one mark and the answer would be another mark. But anytime we see an x or some variable raised to a power of 2 or more, it might not be a bad idea to graph, but I have a feeling that this is just going to be one value. I'm going to graph it here, so let's go to the calculator. So 2x minus 128x to the negative 2. Alright, let's zoom fit. That's funny. So it looks like we do have two values here. I'm going to zoom out instead of zoom fit. Let's see. This looks actually okay. So when we zoom fit, it stretched out the y-axis and not the x. Let me just look at that once again, see if there's anything. It's really peculiar. So 1.74 times 10 to the 5. So it's really stretching out the y-axis, and the x-axis not so much, so it's making it look kind of flat. I don't think this is a very good zoom fit. This is probably better, and we see, although it's changing back and forth, there's only one point where we cross the axis. So analyze graph, find the 0 right here. And when x is equal to 4. So it looks like we could have actually end solved. Let's go back to the document. So in this case, x is equal to 4. For a 2-mark question on a timed test, if you can graph it really quick, but if things are already kind of funny, just it's dangerous to lose time to play with a window, or not to play with a window, but to try to adjust the window to get it right so that you can see the information. A 2-mark question, one is method, one is answer. It looks like this would be our method, and of course this would be our answer. Alright, interpret your answer to B1 in context. Okay, so solve s prime of x is equal to 0. This is when the slope is equal to 0. So let's look at the original question. Surface area of an open box is given by this function, s of x. So the volume is 32, square base with side lengths of x centimeters. So what does this mean? If we found the point at which the derivative was equal to 0, we found either the maximum or the min. Remember, if we're looking at some function and we find where the slope is equal to 0, so something like this, for example, we found the max or the min. In this case, the minimum surface area would just be 0. So in this case, we've found the maximum. And one thing that we could possibly do is we could graph this function. This s of x is equal to x squared plus 128 over x, and see what this value of x4 looks like. That's actually not too bad. And we would find that this is equal to a maximum. Essentially, this is the maximum surface area. So interpret your answer to B1 in context. This represents the point where we have the maximum surface area. All right. Actually, you know what? Let's go ahead and graph this function, because just by looking at this, we're not actually sure whether this is a maximum or a minimum. I don't really want to for a 1-mark question, but let's go ahead and see. So here's our original function. X squared plus 128 over x. 128 over x. Let's zoom out. Okay. And let's look at graph trace. It's a little funny. So graph trace when x is equal to 4. And there it was, just briefly. Graph trace when x is equal to 4. So if this is surface area as a function of the sides of this box, we see that it's minimized. We see that the function is minimized at this point. So when x is equal to 4, our surface area is equal to 48. This is a point at which it's minimized. Alright. So to go back to the document, interpret your answer to be one in context. When x equals 4, or when the side length equals 4, the surface area is minimized. Alright. Let's see how much more there is. I think there's 2 more questions, potentially. Okay. Alright, let's get to it. Okay, here we go. Graph of y equals 6 minus x and y equals 1.5x squared minus 2.5x plus 3 intersect at 2, 4 and negative 1, 7 as shown in the diagram. In diagram 1, the region enclosed by the lines y equals 6 minus x equals x minus 1, x minus 2, and the diagram and the x-axis has been shaded. So what are they saying? Here is y equals 6 minus x, this line right here. X is equal to 1, or negative 1 is this line right here. X is equal to 2 is this vertical line here, and the x-axis. So essentially they're saying that this is this line. X is equal to negative 1. It's this vertical line right here. And x is equal to 2 is this vertical line right here. And we're also shading in, maybe use different colors, we're shading in this whole section right here, essentially. Alright, calculate the area of the shaded region in diagram 1. That's not bad. So it's this function right here, this y is equal to 6 minus x, that bounds the upper part. So if we want to find the area of the shaded region below some function, what we can do is we can use our integral. So numerical integral of some function, so starting ending point of f of x dx. In this case, our starting point is negative 1, and we want to find the area all the way up to 2. The function itself is 6 minus x, and it's in terms of dx. Alright, area of the shaded region. I guess if you weren't sure, you could probably just use triangles and actual shapes, but numerical integral is going to be a little easier. Let's go ahead and work it out. So menu, calculus, numerical integral, starting value of negative 1, ending value of 2, and then we have 6 minus x in terms of dx. But 16.5. Let's go back to the document. Equal to 16.5. Alright. In diagram 2, the region enclosed by the curve y equals 1.5x squared minus 2.5x plus 3, and the lines, again, negative 1 and 2 in the x-axis has been shaded. Alright, so right here, write down the integral for the area of the shaded region. So I think they actually, here they were asking us to calculate the area. Here they're just asking us to write down an integral. So let's see. Let's write it out. A b of f of x dx. So in this case, starting value x is equal to negative 1, going up all the way to 2. So we're going to sweep through this area. So let's write that out. Going from negative 1 to 2. Our function is this one right here. So 1.5x squared minus 2.5x. 1.5x squared minus 2.5x plus 3. And it's in terms of dx. Okay. That's it. Calculate the area. Let's go to the calculator, work that out. calculus, numerical integral, starting value, ending value. Here's our function, 1.5x squared minus 2.5x plus 3. And it's in terms of dx, 9.75. So equals, let's go back to the document, 9.75. Whoops. Put that down here. Hence determine the area enclosed by y equals 6 minus x and y equals 1.5x squared minus 2.5x plus 3. Kind of a neat question. The area enclosed by, this is function 1 and this is function 2. Essentially, they're asking us to find the area enclosed by, so this is where they intersect. Oops. This is where they intersect, right here and here. So they want us to find the area enclosed by here and this function right here. So this is what they're asking us to find. The area that's enclosed by this top function and the area that's enclosed by the quadratic. Okay, not too bad actually. So I guess maybe two things. What's going on here? We found that first area, this area right here, the 16.5, represented all of this, right? And then we found out this area under this quadratic, I'm going to erase this, which represented, let's get a new color, let's use green, which represented all of this essentially. And so if we call this, let's say, maybe I can use even a thicker brush or so. We call this A1. And if we call this, for example, A2, what do we know? We know that A1 minus A2 should give us the area of the enclosed region. So A1 is everything below, right? It's everything below here, so on. And if we take out area of A2, this green region right here, and so on, we're only going to be left with this right here. This, what can we say? The area enclosed between, let's say, area enclosed. So what is it? It's 16.5. 16.5 minus, we said 9.75. And this is going to be equal to, once we work it out, 16.5 minus 9.75 is going to give us 6.75. Kind of a nice question. There it is. All right, last question, 15 marks. 15 marks, okay. All right. All right. A sector of a circle, center O and radius 4.5 is shown in the following diagram. Find angle AOB. Okay, not bad. AOB, remember start at A, go to O, and then go to B. They don't tell us what kind of triangle it is, but since it's part of a circle, if this is a radius, then this would also be a radius. So we know two side lengths. Actually, sorry, we don't even need to know that, really. Since we have one side length right here and another side length right here, and we know that it's a right angle triangle, we should be able to just use our plane trig ratios. And if we know that's theta, then this is theta, and we can just multiply it by 2. So, what do we have? We have an adjacent side length. So we have an adjacent side length, and we also have the hypotenuse. So remembering sa, ka, toa, this actually isn't given in the formula booklet, your trig ratios. But if we have an adjacent and a hypotenuse, then we're dealing with cos cos theta. So the adjacent is 4, and the hypotenuse is 4.5. And after that, you can end solve for theta. Make sure you're in degrees, of course. I'm going to work this out on my calculator beside me. And then we have cos theta, and it looks like theta is equal to 27.26 or 27.3 degrees. Not bad for a, whoops, sorry, I'm not quite done yet. Not bad for a 3-mark question. This is only equal to theta. Of course, we want to sweep through an angle of 2 theta. So therefore, 2 theta is equal to 54.5. Actually, best not to write 3 sig figs as an intermediate step because you'll get an error. So this was 27.266, for example. 266, and we multiply it by 2, we get 54.5. Okay, so therefore angle AOB is equal to 54.5 degrees. Okay, find the area of the shaded segment. 5-mark question, kind of nice, I think. All right, area of the shaded segment. So they're asking for this portion right here. Okay, interesting. Okay. So I'm going to actually erase most of this here and then sketch it up new. Okay, so what do we have? We know that this angle theta is equal to 54.5 degrees. So we don't have a whole circle, we only have a partial circle. And what do we have? We can find the area of this partial circle, right? And we can find that area of the partial circle using the area of a sector. So let's actually just go ahead and do that. I'm actually going to erase this other portion right here because we don't need it, and I feel like we've got the information we need, and it's just going to be easier if I can show everything here. So we want to find the area of this shaded segment, this part right here. Okay, so let's find the area of this blue part. We know we can find it by just finding the area of a sector. So area of a sector is equal to theta over 360 times pi r squared. We don't have a whole circle, we just have a fraction of it. So 54.5 over 360 pi, and then our radius, the distance from the center to the edge of the circle, right? This circle would have been like all the way through here or something like that. Distance from the center to the edge of a circle is 4.5. So pi r 4.5 squared. So that would be the area of the sector, and I'm going to work it out on the calculator that I have here. 4.5 squared times pi, and then times 54.5 over 360. We only have a portion of this. Alright. And this gives us a value of 9.631. That should be enough digits for now, I suppose. Okay, so that would be the blue. And we know if we take the area of the sector, the blue, and for example we subtract this triangle, then we should get the area of this shaded portion. Okay, so how do we find the area of a triangle? We know the base is, which we don't know the base, but we know the height is equal to 4. So we know, for example, that area of some triangle is equal to base times height over 2. We know the height is equal to 4. Actually, you know what we could even do? Maybe even nicer, to be honest. There's two different things we can do. We can use Pythagorean theorem, And remember, Pythagorean theorem says if you have some right-angled triangle, A, B, and C, we can take a squared plus b squared is equal to c squared. And then looking at this, we have the hypotenuse, so we have 4.5 squared. We have one of the side lengths, so we have a 4 squared. And the question is, okay, well, what's a squared? And you can end solve that. The other way is we have the area of a triangle. We have area is equal to half AB sine C, right? So if we have some non-right angle triangle, any kind of triangle, and we have A, B, and then the included angle here, we can just use half AB sine C. That actually might be a little smoother, I suppose. You can do both, really. Find the value of A, and then multiply by 2, and then you have the base, right? So this would just give you portion. I want to multiply by 2, then base times height. Or, I think this is the way I'm going to solve it. It's just using this area of a triangle formula. Since we have 4.5, and we know that this is 4.5, because they're both the radius, we have two side lengths, and we know the angle in between. So I think that's the way, I think I'll solve it that way. Okay, half A is 4.5, B is also 4.5, and then sine, we said it was 54.5, so 54.5. And that should give us the area there. So sine 54.5 times 4.5 squared times 0.5. And this gives us a value of 8.243. Alright, so if we have the area of the sector and we subtract the area of this triangle, let's write that out. Area of the sector minus the area of the triangle, we should have area of the shaded region. Area of the shaded region. So 9.63 minus 8.243, 9.631 minus 8.243. This would give us a value of 1.388 or 1.39. Okay, there we go. There's a goat. Okay. I think that's it. Okay. A square field with side 8 meters has a goat tied to a post in the center by a rope, such that the goat can reach all parts of the field up to 4.5 meters from the post. Okay. That's interesting. So 4.5 meters. This, of course, matches this 4.5 meters. It's a paper 2 question, so we gotta go back to earlier parts of the question often. All right. Find the area of the circle with radius. Find the area of a circle with radius 4.5 meters. Okay. I guess it's the example of paper 2 questions also having kind of discrete portions. So area is equal to pi r squared. Area is equal to pi, radius is 4.5 squared. Nice kind of question, I suppose. 4.5 squared times pi. This is just going to give us a value of 63.6 meters squared. Right. Nice, generous 2-mark question. Find the area of a circle with radius 4.5. Sure. Find the area of a field that can be reached by the goat. Alright, so the area of the field that can be reached by the goat. So here's this goat, and what does the goat do? Can go and he wants to get some food. Okay. And there he is, but we see that the goat can't get all of the food. So we want to find the area that can be reached by the goat. And what we see is that we have this situation. we have the situation where the goat can get a certain amount of food. Whoops. Let me reduce that. So the goat can get this section right here, right? But they miss out on this shaded portion. And the goat can also get this portion right here. But they actually, sorry, this is a terrible kind of drawing. Let me go back and modify it in a way that I think is a little more accurate. Okay. So let's use this as a center. And something like this. And I'll change this if I can. And put this in the center. And let's make this in the center a little more so it a little more accurately reflects what's going on here. Something like that, I suppose. Maybe a little smaller. But anyways, I think we have the general idea now. Okay. So there's some area that the goat can get to, right? The goat can get to all of this area right here, but there's this shaded region once again that they can't get to. And same here. There's this area that the goat can get to, but there's this shaded region once again that the goat can't get to. This portion right here. The goat can't get to this. So what can the goat get to? Let's actually complete this, because I think this is actually a pretty nice question, to be honest. Okay, so here we go. Oops. Alright, so we see that the goat can get to everything essentially within this circle. There's some parts that they can't get to though. They can't get to this, and they also can't get to this. So this is kind of interesting. When he marks this, is find the area of the field that can be reached by the goat. The area of the field. So we actually don't need to worry about this because we only need to find the area that can be reached by the goat. The goat can reach everything within this circle. So the goat can reach, if the goat was in an open field, it would be able to reach 63.6 meters squared of field. But it can't because it's missing out on these shaded sectors. And we know if we go all the way back here, the area of these shaded sectors is 1.39. So the goat can get everything if it was an open field, but it's missing out on these 4 sectors, each with an area of 1.39. So that seems not too bad at all, actually. And that would be the area that can be reached by the goat. So 63.6 minus 4 times 1.39. And that means the goat can reach 58.06 or 58.1 meters squared. And I suppose we can hope that that's enough. Alright. I think the second last question. Let V be the volume of grass eaten by the goat in cubic meters and T be the length of time in hours that the goat has been in the field. Okay. The goat eats grass at a rate of, okay, change in volume as a function of time, or change in volume over change in time, equals 0.3 T e to the negative t. Wow. Find the value of T at which the goat is eating grass at the greatest value. The value of T at which the goat is eating grass at the greatest rate. So this function represents the rate at which the goat is eating grass. And we want to find the value of T at which the goat is eating grass at the greatest rate. Wow. That's interesting. This is almost like a higher level question. Jeez. Okay. So this is the rate at which the goat eats grass. And we want to find the value of t at which the goat is eating grass at the greatest rate. So, I mean, this is essentially what is going on. This is the end of a paper too, so it's very, very challenging. This is the rate at which a goat is eating grass. T e to the negative t. And you know what, actually, I was thinking we can take the derivative of the derivative, but let's just sketch this and find out where it has a maximum. I think that's going to be a lot easier. So let's go into the calculator screen. So 0.3, let's say this is x, and then remember this e is not a variable, it's actually just a value. Whoops, sorry, let's get a new document here. So this is 0.3x, and then this is e to the negative x. Let's find out when this reaches a maximum. So analyze graph, and then let's find the maximum right here. And it's at the point when x is equal to 1, the rate is equal to 0.11036. So find the value of t at which the goat is eating grass. Let's go back to the document here. When t is equal to 1. Okay. And then, of course, 2-mark question. Might want to sketch this out. Something like this. And then something like this. And we could even put when t is equal to 1, and these were the values here. This is equal to 0.110. That's okay. Okay, and that was it. Wow. That was it. Kind of anticlimactic in a way.